Thank you very much. I want to thank the organizers, especially Jürgen, for inviting me here. It's lovely to speak here. So I need to first briefly introduce my background. I think I came from a very top skill, macroscopic skill. I was trained in the Department of Automotive Engineering, working with batteries, fuel cell vehicles. And then step by step, I find myself on this atomistic skill, trying to understand what is happening on the bottom skill. So this is approach. It's just a name, a density potential functional theoretical approach. We try to put potential on the same equally foot as a density in the approach, because electrochemical reactions, all the processes occurs at a constant potential. So this is a quite recent approach we have been developing since 2022. So I'm going to introduce our very recent and preliminary results. So your feedback really will make an impact on my research. For instance, last October, I gave a talk in Fritz Haber Institute, and Professor Ritter gave a comment on benchmark of this approach and this result in one section of this presentation. So I look very much forward to your feedback and suggestions. So this is today's, agenda. I first introduce the background and give a glance at the approach. And then I wanted to explain the theoretical foundation of the approach, and then how to benchmark this approach. And also, I would like to connect with realistic electrodes. I want to thank the people I work together in my group, and also the funding agencies from Helmholtz and also European Research Council. And my main collaborators on this program is Professor Eikening, Professor Yan Chen in Hefei, and also Professor Marco Milander in Finland. So one of the motivations of this to develop this approach is actually the three-body problem in electrochemistry. So we have catalyst, we have electrolyte, and we have support materials. And in some cases, in batteries, we have active materials, we have electronic conductors, and we have electrolyte. And actually, heterogeneous catalysis, from my perspective, focus on the interaction between the catalyst and the support. So we have many scenarios of these interactions. And electrocatalysis, on the other hand, focus on the interface formed between the catalyst and the electrolyte. And we have talking about this interface a lot in this workshop. But there's actually the support account for the majority of the interfaces in electrodes. And this how support and electrolytes interact and how these interactions influence the overall local reaction conditions. So this is the major motivation for this approach. From our perspective, the key theme in this scenario is overlapping double layer. So we have double layers formed between this nanoparticle and the electrolyte solution. So this TM is taken from in vacuum. So actually there is a solution. We imagine there is a solution. But there's always an interface between the support and the electrolyte solution. And because these two interfaces exist in a close proximity, so they overlap. And to resolve this picture, it is a challenge for theoretical people. For instance, we need a unified treatment of both quantum mechanical electrons, because electrons may usually exchange between the support and the catalyst and the support. And we also need equally a theories treatment of the classical particles like ions, like solvent molecules. And the approach in this case should be computationally efficient, because we want to simulate interfaces on the mesoscopic scale on 100 nanometers. And it should ensure the system consistency. That means we want to simulate the interface at the potentials measured in experiments. And we need to treat reactive surface because on the nanoparticle surface, there are electron transfer reactions occurring. And so ideally, the surface, usually the surface is far away from equilibrium. We have to treat these non-equilibrium conditions. And there, of course, it's a common challenge. There have been a lot of works in the field. For instance, the quantum mechanical DFT approach is the workhorse method. But to treat this kind of problem, we usually, because the computational cost is very high and scales usually cubically with the number of atoms considered in the calculation. So we use simpler systems. For instance, in this recent article, these two photos, these two pictures are taken from the same study. But to simulate the interface, they can only simulate a very small nanoparticle to capture the essential of physics. Or in this work, there is no account for the liquid. So in general, density functional theory gives a poor statistics of liquid. So we have been developing implicit solvation method, for instance, from Richard Hennig. And so this is one option, but it's difficult to simulate the whole system under electrochemical conditions. And there's also continuum models, and the continuum models help a lot in understanding the overall picture. For instance, in this work from Arendt, they simulate the platinum nanoparticle on carbon, and they simulate the potential distribution between nanoparticle and the support. And for instance, Manuel also introduced, not related to this structure, but they simulate the heterogeneous distribution of potentials from between different surfaces. But in these simulations, there is no electron ionic coupling effects. So the matter electronic effects are taken into consideration in the boundary conditions. We assign a potential of zero charge for different surfaces in these studies. But in this problem, the atoms here, there, they may have different potentials of zero charge. So this require a consistent treatment of the whole problem. But we have been developing this approach. The basic idea is we need a equal treatment of the electronic effects and also the liquid effects. For the electronic effects in this ground canonic potential, we use the orbital-free DFT for this. So this is an old method, or the first version DFT actually. And the basic idea is to describe the distribution of delocalized electrons. And this is how these delocalized electrons influence, shape the overall local reaction conditions. And then for the liquid, we use statistical field theory. So we introduce electric potential, polarization field, and their gradients into the ground canonic, the ground potential. And for their short-range correlations, which are important for adsorption effects, we use the empirical pairwise potentials. So this method is efficient for electron-ion dipole interactions under ground canonic conditions. And because we have electron density and electric potential in the functional, then we call it a density potential functional theory. I want to give a very quick introduction about the results of this model. So this is a one-dimensional structure between a metal and electrolyte solution. So this is the interface. And this is the distribution of the electron density. Inside the bulk, we have these oscillations due to the periodic arrangement of metal atoms. And the electrons speed out from the metal edge into the solution. And here we have 5 curves because we changed the electrode potential. And we will see how the electron spillover is tuned by the electrode potential. And we also, the model can give the polarization field. So this is basically the water density multiplied by their average orientation angle. And you see their oscillations, and you can imagine that this orientation of water molecules will give rise to oscillations in the local electric potential. Inside the metal, the potential is not influenced by this polarization field, but in the local, within 1 nanometer, these oscillations will be very important to describe the local reaction conditions. And because of this, then the model can give the distribution of cations. They form layers in the solution, and how they change with the electrical potential. So this is for anions. And the model can also give the distribution of the solvent density at the different potentials. So this is a kind of state-of-the-art of continuum modeling of electrochemical interfaces with a coverage for these electrons and also ions and the solvent molecules. So this is in 1D, and it takes a few minutes to simulate the interface on personal laptops. And we can apply this approach to the beginning problem, but here we treat a toy model. This is a silver nanoparticle on gold. And we use this because for silver and for gold, we have a very good capacitance data, so we can benchmark the data very well, the model very well. So, And you see this is under the overall potential of zero charge. So the surface is uncharged. But you could, because the gold and the silver, they have different work functions. And so electrons will be transferred from silver to gold. So you see the silver nanoparticle is positively charged and the gold surface is negatively charged. So they will naturally give rise to an electric field pointing from silver nanoparticle to the gold support. And with the model can also simulate the interface in the solution phase. And you see on the same scale, the electron transfer is enhanced. And because silver is positively charged, so there are a lot of anions here, and because the gold support is negatively charged, we have a cation accumulations here. And then I will explain, because we have mathematicians in this audience, I wanted to explain the theoretical foundation, starting from Cochamp DFT and then to our DPFT. This was the work did by Menke and Xiwei. And actually, we recently came up with a systematic derivation from many electron theory of condensed matter to this DPFT. The first scheme is the starting point is we're using Cochamp DFT for all atoms in the metal and all atoms in the solution. So this is our starting point. And then, because there's no reactions in the solution, we can use orbital-free DFT for all atoms in the solution. So then we retain an electronic description for the solution. The third case is we don't want to solve for the electron density in the solution. We can assign electron density distribution for all atoms. So this is called frozen density for all atoms in solution. The fourth scheme is we use a statistical field theory to describe the solution phase. And we keep the Cochamp DFT for all atoms in the metal part, and including the reactive surface. And if we wanted to reduce the computational costs, we can use orbital-free DFT for non-reactive atoms here, and we only retain a Cochamp DFT distribution for reactive surface in the first few layers. And for the liquid solution, we use statistical field theory. And so this is the agenda, and I will then give a little bit more mathematical derivations. So this is the starting point, and the total energy, including electronic part, including kinetic energy of electrons, exchange, external, and also the electrostatic interactions between electrons. And this is the nuclear energy, nuclear kinetic, electrostatic external energy of the nucleus. And then for the in Cochamp DFT, the kinetic energy is approximated using a Cochamp scheme. We can calculate the auxiliary orbitals, and then we can get the kinetic energy, and we can find the electron density. And this is costly in calculating the Cauchy orbitals, and it's give a poor statistic of the liquid, as I mentioned in the beginning. And in this case, statistical field theory can help with the statistical sampling of the liquid. So this is the starting point. And then we can use orbital-free DFT for the liquid part because there's no reaction there. And the basic idea of orbital-free is that we express the kinetic energy as a function of the electron density. So in this case, the total electron kinetic energy is divided into the kinetic energy of orbital-based NOB, orbital-based electrons, orbital-free electrons, and there is a non-additive term. And because of this, then we need to change, there's an additional term in the effective potential for electrons. So we can further simplify the calculation by using frozen density embedding scheme developed by Professor Owasa many years ago. And we can also transfer from electron density description from a particle-based description to a pairwise potential or force description. This is key in transforming from electronic structure calculations to field theory. And then with this, then we can write the overall partition function of the whole interface, which is divided into an electronic part and a nuclear part. And for the electronic part, because we know the free energy of the electronic gas, then we can write the partition function of the reactive part. And the difficult part here is the partition function of the non-reactive electrolyte solution. And it's complicated, I try to explain. So there are one-body terms like the external potential will change the distribution of these charged particles. So this is one particle term. There are interactions between charged particles. They have, so this is electrostatic interactions with the Green function for the Coulombic interactions. And in addition to that, we have short-range interactions. This is how we have these steric interactions, mechanical effects, and all this. And here we use a general kernel for this. And this kernel could be like a hard sphere interactions, or you can use expansion in different orders. So this is the charge density in the system, including electrons, all the nucleus, and also the dipoles. So this is difficult to simulate because this is particle-based. And with field theory, we can transfer, for instance, from this this is the electrostatic part to a field-based. We introduce an electric field in this calculation. And similarly, we can do the treatment for the short-range interactions, and we introduce steric potentials. So these steric potentials, they actually account for the short-range interactions, not beyond the mean field electrostatic potential. So this is, and then we obtained a ground potential, which is a hybrid functional of densities and potentials. So that's what. This is why we call it a density potential function approach. And with so this is the expression for the overall partition function. It's written as an integral over all these oscillatory auxiliary potentials, electric potential, steric potential, and this S is the action. And this action is divided into a quantum part, electric field, and the steric potentials, and the single particle atoms. So these are the different items. And from this, then we can use variation analysis to derive governing equations for this density and the potentials. And also from this, we can calculate the electrochemical potentials of all these species. And it would be interesting to map these electrochemical potentials of ions into this chemical and mechanical part. This is interesting. And this is other equations for the density field, electric potential field, steric potential field, and in this case, we retain an orbital-based description for this, so this is just Cauchy DFT scheme. And for electrical potential, we have a modified Boson-Boltzmann equation. And you see it here, then the permittivity becomes a function of the solvent density and the local electric field. And the steric potentials are new in this model. They describe the short-range repulsions between particles. And in general, it can put in this way. But if we only consider the repulsive part using the Morse potential, then we obtain a fourth-order differential equation for this steric potential. And so this will lead to oscillatory density profiles in the interface. And in this model, then these ion densities are determined by the interaction with the metal electrons, electric potential, and also auxiliary, this steric potential. And this is for the expression for the solvent density. And recently, we came up with a proof of concept model for this. So this is for the electron density. And we get different levels of eigenvalues. And we add up to infinity, and then we get this electron density. So this is a 1D, one-dimensional Jelian model. But in this case, we obtain these phase oscillations in the interface. And this model, can be calculated at a given electrochemical potential of electrons. And then we can also get the steric potential for cations, because at this potential, the surface is negatively charged, a lot of cations in the interface. And so the steric potential for cations are positive. They try to reduce the cation density. And then we compare the capacitance profile with steric potential or without steric potential, and the steric interactions will reduce the capacitance when the surface is highly charged. And here, we didn't introduce potential zero charge because the model can calculate. So the potential zero free charge is not a parameter here. It can be calculated from the theoretical model. So that's it. And then the model is a field description, and we need to benchmark the parameters. And okay, so and previously I introduced the orbital involving DPFT, but we also have orbital-free DPFT. That means we use the orbital-free description for the electrons. So this is a Thomas Fermi von Weizsäcker function for the electrons, and these are the PBE function for the exchange correlation terms. And for the solvent here, we introduce the polarization field, and we include the short-range interactions between this solvent in using three parameters, KRS, K alpha, K beta. And we also include the short-range interactions between the solvent and also the ions. Using two parameters, alpha A, alpha C, we need to determine this later. So this is for the long-range Coulombic interactions, for the configuration entropy. And this excess free energy is actually related to your pressure. And we also consider the short-range metal solution interactions, and this ensures that the simulation is conducted under ground canonic conditions. And with this functional, and then we can do a variation analysis. So this is the controlling equation, the second-order differential equation for electrons. And then we can do the same for the electric potential. And here we don't use the permittivity because we have the polarization field. So with this, then we can consider the non-local electrostatics using this P field. And this P field is related to this auxiliary field. And so you could say this polarization field is determined by a fourth-order differential equation that we would expect oscillatories from this formalism. And if we do the variation analysis for the cations, anions, solvent, then we get the expression for the electrochemical potential of these particles. So this is the expression for the cations. And we could identify an entropic term, the electrostatic term, and also the short-range interaction between this cation and the solvent. And also at the interface, they interact with the metal. And we can do the same for anions and the solvents. And the equilibrium, all the electrochemical potentials are uniform, and then we can calculate these density fields as a function of these potential fields. So this is a summary of the DPFT with short-range correlations equations. Basically, we need to solve 4 equations. And if we neglect these short-range correlations, that means all these short-range parameters are 0, and then the polarization field is actually a function of the local electric field. And then we only have 2 equations. So this is our DPFT in mean fields. 1 equation for the electron density, 1 equation for the electric field. And in many cases, we can also neglect the electron density, then we only have the modified Boson-Boltzmann theory. And we use a divide, conquer, and reintegrate strategy to benchmark the 3 components. For the orbital-free part, we developed a Cauchy DFT for this in 1D to reduce all the structural complexities. So this is, I think, is ideal for this benchmark. And for the statistical field theory, we can use the bulk properties of water and ions, and then we can determine all the parameters in the functional. And for these pairwise potentials, we integrate them together when we use experimental W capacitance curves. So let me start with this, the first part, the orbital-free, how to benchmark the parameters in orbital-free DFT. For instance, in this, if we use the Thomas Fermi von Weizsäcker, there is a gradient term, gradient coefficient, and how to get the gradient coefficient there. So for this one-dimensional interface, we can simulate the electron density, normalized electron density, normalized to the Bach value. So, and this 0 means the interface. Below 0, it is a Bach metal. This is in the solution, and this is at the potential 0 charge. So we can calculate the electron density distribution for 2 models. One is the Cauchy Boson-Boltzmann equation. So this is the benchmark, and this is the orbital-free version. And we calculate that difference with different parameters in the orbital-free part. And you could see in the interface is positive. That means orbital-free method overshoots on the metal surface. The electron spillover is more extended. But it's just 2%. And we can also calculate then the W capacitance profile as a function of electrochemical potentials of electrons. So those dots are the benchmark results, and these lines are the orbital-free models with different gradient coefficients. And we could say when the gradient factor is 0.7, and then we can predict the potential of 0 charge. And this value is much smaller than the default value in the Thomas Fermi von Weizsäcker theory. So this is for the first part, and then for the second, and in the description for the liquid, we have 3 parameters, Ks, K alpha, K beta, to describe the short-range interactions between these water molecules. And also for the short-range correlation between ions and the solvent, we have 2 parameters. How to determine these 5 parameters in total? So we first work on the pure water. And for pure water, we have this non-local dielectric response. And this can be measured, this can be calculated from MD or AMD. And in our theoretical formula, so this susceptibility function is wavelength dependent. And it depends on 2 parameters. And this function will give you a peak. And if we know the peak of the wave number, and we also know the peak susceptibility, then we can calculate K alpha, K beta. So I just want to show our own MD simulations. For pure water, we get these two parameters, we substitute into these expressions, then we have K alpha and K beta. And then we use these in the simulation of the interface. And for ions, there are a lot of data on the hydration-free energy. This is for cations, this is for anions, the hydration-free energy as a function of a radius of the ions. There is a very interesting phenomenon, much discussed in the literature. Consider potassium and fluoride. So you could see their radius is very similar, but their hydration-free energy is very different. And this can be captured in our theory using this. We consider the ions and the anions, they have different charge distribution. The anions, the charge distribution is more local, and for these cations, they are more extended. So we use a small Gaussian distribution in calculating the hydrogen-free energy, and they have different n numbers. When this n is bigger, that means we have a more like a data function distribution of the charge. So you see for these cations, this n is smaller. That means the charge is more broader. Charge distribution is more broad. And this alpha describes the short-range interactions between ions and the solvent. And for cations and anions, they are different. For cations, they are slightly more negative. That both of these two parameters means the cations push water molecules further from the cation surface. And then we use the W capacitance data to benchmark the short-range interaction parameters between the metal and the ions. And here, we did many benchmark studies for different systems, for instance, for mercury in aqueous and non-aqueous solution, for silver single crystals in aqueous solutions, and also for gold non-aqueous interfaces. Here, I just want to give an example for this silver and the gold in this aqueous solution. I like this experiment data very much because they are from different groups. So silver is from Valetti, and the gold is from Hameni. And they use the same facet, 110, different metals. The solution is quite similar, 5 millimolar or almost 5. And you could say after correcting their different potential zero charges, the capacitance curves match exactly. And it's very difficult to achieve this agreement for platinum, for other metals. But for silver and for gold, they can achieve this. And so the dots are experimental data, the curve are the model results, and the key parameter in this model is the distance between the first layer water and the metal surface. And we know silver is hydrophilic, so the distance between the silver surface and the water molecules is smaller. This A0 is the Bohr radius, so the distance is about 2 Armstrong. And for gold, it's hydrophobic, more hydrophobic, so the distance is larger, and this will explain why the peaks for the capacitance peaks for gold is more separated. So here I want to say that in our view, the peaks are not due to L-Courant, it's due to the reduced water permittivity caused by the orientation or polarization saturation. And using the same parameters, we can predict the capacitance curves at a higher concentration, and a very good agreement between the model and experiment is achieved. And then I wanted to, with the benchmarked model, I wanted to connect with realistic electrodes. And this was the work did by Wei Qiang and Zheng Ming. And we look at irregular electrodes with roughness, with step, kinks, and roughness. So in Zheng Ming's work, we simulate the double layer with steps. So this A0 is the Bohr radius, and you see the scale is about several nanometers. And this is the metal, this is the solution, is for electron density. The model can give the distribution of delocalized electrons. These are not the total electrons, just the delocalized sp electrons. And you could see the electrons are a little bit less in the peak, and more electrons can be found in the valley. So this is a norm effect. And this will change the distribution of cations, even though the surface overall is electroneutral. And we could find more cations in the valley, and then more anions near the peak. And with this, then we can calculate the potential of zero free charge PZFC change as a function of step density for silver and for gold. And you see the PZFC decrease moves in the negative direction as a function of the step density. And those symbols are the experimental data in the literature, and the model with considering only the delocalized electrons can capture the PZFC changes. And we can do a little bit more. We can calculate the stress of the surface. And in here, we consider a phenomenon called step bunchening. So here we have two surfaces with different step density. So here we have smaller steps, and these two steps can combine into a larger step. And experimentally, it is observed that this can occur at some potentials. So we wanted to know the thermodynamic origin. So we calculate the free energy of the whole interface for the two configurations. And so this is the free energy change at the different potentials for different densities. So if this one, B, is smaller than this one, that means this is more stable. And we find at high densities, at more positive potentials, this indeed is more negative. So that means step bunchening can occur for very dense, for electrodes with dense steps and at more positive potentials. And this is observed earlier in Leiden in Mark Cooper's group for platinum. So our model is calculated for silver and gold, but the experimental data are for platinum. So be aware of this difference, but the phenomena is there. And then the second application is to rough surface. And for atomistic roughness, on the atomic scale, we can use Cochem DFT to calculate how the roughness change the work function and the double layer. At a higher level, so people have been using the Poisson-Nernst-Planck theory to describe the mass transport effects at rough surfaces. But we are interested in somewhere in between. And in the mesoscopic scale, both electrons and solvent molecules, ions, they are equally important. And we are using our approach to study the mesoscopic rough surfaces. First, we calibrate this with Cochem DFT using work function. So the work function decreases when the surface gets rougher. And so this parameter is the distance between the two valleys. And this parameter is smaller, that means the surface is rougher. And you see there are less electrons in the peak and more electrons in the valley. And because of this, there is a counter dipole formed at the interface. This will decrease the work function. And there have been a relationship between work function and the potential of zero free charge. And then we would expect a correlation with a slope of unity. But because we can simulate both vacuum and solvation interfaces, we found that the slope is much smaller in our model. And Katarina and Jun Huang calculated two interfaces using ab initio molecular dynamics. And their slope is also smaller. And we tried to understand this, and we found permittivity, interfacial permittivity is very important. So this is the local electric field distribution. In the valley, the field is very big. So this will reduce the local permittivity. When the permittivity is smaller, the electric potential drop at the surface will be bigger. And that will reduce the potential of zero free charge. And the third application, as I mentioned in the beginning, is the overlapping double layer at supporting nanoparticle catalyst. And I have expanded this before, and then we also did a benchmark with using the implicit Vaspasol, but on a much smaller system. So this is silver nanoparticles on God, and this is DFT in vacuum with Vaspasol to also consider the solvation. And at uncharged surface. And this is our method. Quantitatively, they agree with each other, but our model, we don't consider the atomic structure of atoms in the solid, so we didn't see these fine structures. But over we see there is a charge transfer from silver to gold, and the charge transfer is enhanced in electrolyte solution. And very interesting, in this case, the potential zero free charge is not applicable. And we have to define new characteristic potentials. So for ideally planar surface, potential zero charge guarantees both electronic and ionic excess charges. But in this case, we need three potentials of zero charges. So at the potential of zero charge of the nanoparticle, the surface is actually charged. For instance, the silver is positively charged, and there are a lot of cations. Counterintuitively, there are a lot of cations nearby, because these cations are not introduced by silver, but by the negatively charged gold nanoparticle. And if we shift the potential more negatively, and we see then the excess electronic charge on the silver nanoparticle is zero. So this is the potential of zero local electronic charge for this system. And if we move more positively, then the excess ionic charge above silver is zero. So then we have this log of zero local ionic charge. And the difference between them is a function of the bulk ionic strength. When the solution is very dilute, the difference is very big. And when it becomes more and more concentrated, then the difference becomes, the potentials came closer to each other. So here is the main takeaways. We have developed orbital-free, and we can also consider a few orbitals in the system, approach to provide a ground canonical simulation of electrons, ion, dipole interactions on the mesoscale. And this method, we consider the metal electronic effects, the steric interactions using the steric potential. So this steric potential is governed by a fourth-order differential equation that is derived rigorously from the pairwise force relation. And we consider the solvent polarization field and how the solvents interact with each other, and the interactions between solvent and ions. We have been applying this approach mainly to mesoscopic double layers, the double layer with steps, and also the overlapping double layer in supporting nanoparticles. And as I mentioned, we have been developing this method in 3 years, so they are very preliminary results, and we are developing this very quickly. We try to apply this to a wide range of materials to consider the different density of state profiles, for instance, graphite. And we are extended to non-equilibrium dynamic conditions and to consider chemisorbates. I wanted to use 1 minute to introduce our recent work in these non-equilibrium conditions. And but the feature of our work is we have these electron-ionic interactions. And experimentally, people have been using plasmonics to probe, to modulate electrochemical interfaces. And this can actually be captured by our theoretical approach. And there is no theoretical models for electrochemical plasmonics. So Lulu has been extending our approach from equilibrium to these non-equilibrium conditions, and we have, this is for the, you could say the equations in the frequency domain. That is, we do linear response analysis for the electron motion and how they coupled with ion motions. And then we can calculate For instance, at the different frequencies for this nanoparticle, if you perturb the surface with electromagnetic wave, how the electron density, the real part, the imaginary part, electric field change with the frequency. And from this, we can calculate the absorption spectrum as a function of a nanoparticle size and also as a function of potential. So this is known. The particle size effect can be, at a larger scale, can be calculated using electromagnetic models or TDDFT models. But in this mesoscopic scale, from 10 nanometer to 30 nanometer, there is other methods that are difficult to do this. So these are the related experimental data we try to understand. So this is unpublished, ongoing work. Thank you very much for your attention. Yeah.